We will finally talk about coverage effects. In general, adsorbates on catalytic surfaces form non-ideal add layers. This is contrary to the case of the model we discussed in the previous lecture, the Langmuir isotherm model. As you may remember, in that model, a fundamental assumption was that adsorbates do not exert lateral interactions between each other, whereas in reality, this is probably not a good assumption for several realistic systems. So in these systems, adsorbates do exert attractive or repulsive interactions. So these interactions give rise to non-ideal add layers. And eventually, the consequence of that is that the total energy of the add layer is not necessarily equal to the sum of adsorption energies for the adsorbates on the lattice. So here is an example, a small lattice, which we will assume that it's not periodic. So we have 4 adsorbates on the lattice, and if the add layer was ideal, then the total energy of the lattice would just be 4 times the energy of adsorption of the single body. However, in the general case, we will also have contributions from higher order terms. So 2 body interactions like these ones here for the first nearest neighbor interaction. So we have 1, 2 first nearest neighbor pairs plus terms for the second nearest neighbor interactions. Again, we have 1, 2 second nearest neighbor pairs, etc. So these may be longer range interactions or many body terms that involve, for example, 3 adsorbates, etc. So in general, we can write an expression that gives us the total energy of the lattice. So this is called the cluster expansion. I'm using this Hamiltonian notation here because really this sigma is my the variable for my microstate. But note that this Hamiltonian, it may be a bit of an abuse of the terminology, because in general, in the cluster expansion, we can capture functions that may be free energies, for example. So the single body term over here may also include vibrational contributions, making it a free energy rather than just a potential energy. So when I say Hamiltonian, this is in the context of kinetic Monte Carlo, but just keep in mind that this thing may be a cluster expansion that gives me some sort of free energy for my lattice as a function of the configuration, the occupancy of the sites. So what is this equal to? It's a sum for k equals 1 to nc. Nc is the number of clusters that we have on the lattice. ECI is the effective cluster interaction. It's basically the contribution to the energy of the system of that cluster. GM is this graph multiplicity. So this is really an algorithmic kind of parameter. So in some cases, when graphs like this are symmetric, they are detected twice. So then I would have to correct for the double counting, and this is what the graph multiplicity takes care of. And this NCE is the number of instances of interactions pattern K. So in this case, for example, for the two-body interaction, the nearest neighbor interaction, I have 2 distinct patterns. The graph theoretical kinetic Monte Carlo algorithm would detect, because of symmetry, 4 such patterns. So graph multiplicity is equal to 2 because each one is detected twice. So then I would have this 4 divided by 2 equals 2 times this E, which is the effective cluster interaction of that pattern. So just to give you an example, this could be, for example, 0.1 electron volts energy penalty corresponding to a repulsive interaction. So every time I see a pairwise pattern like that, I have to add 0.1 EVs to my total energy of the add layer. Now, the patterns are represented as graphs, so they can be detected using the same ideas that we discussed earlier for reactions, using a subgraph isomorphism solver, etc. So why do we care about attractive or repulsive interactions? Because they affect the rate. So I mentioned a few minutes ago that depending on the spectator configuration around the reaction event, we may have attractive or repulsive interactions between the reactants and the spectators, and this could influence the rate constant of the reaction. So let's look at a very simple example here, in which we are looking into the rate of desorption of a species. So by the transition state theory, which is really a version of the Arrhenius equation, this rate for the desorption is equal to a pre-exponential, which we know how to calculate, times e to the minus activation energy over kT. But now I have this term which takes care of the lateral interactions. So this times sigma I. Of course, when sigma I is 1, this means that the site is occupied, so desorption can happen. When sigma I is 0, desorption cannot happen. Of course, you cannot desorb from an empty site. So let's focus on this term now. And let's assume that there are repulsive interactions in our system. Therefore, this J int, right, this J parameter for the interaction is positive. So when the desorption happens from a site which is surrounded by empty sites, it will happen with a rate equal to A desorption times e to the minus activation energy over kT. You see that this sum is sum of the occupation variables in the neighboring sites, right? So J is in the neighborhood of site I, and of course, since there is nothing in the neighborhood, these sigma i's are all 0. Therefore, this activation energy is just equal to EA. Now, let's say that at some point in the simulation, an adsorbate happens to appear on the neighboring site 1 of site I. So what is going to happen in this case? If we reevaluate the expression, we will realize that this sum is equal to 1. We have one neighboring adsorbate. So this would be activation energy at the 0 coverage limit minus J int, right? So the interaction parameter. If we if this is repulsive, J int is positive, and therefore the activation energy for the desorption is reduced by a factor of J int. Does this make sense? Yes, it does. If this adsorbate is in the presence of a field that exerts repulsion on it, then of course it would have a higher propensity to get out of there, go to the gas phase, because it feels the repulsion from that adsorbate over here. And we realize that if we start placing more and more adsorbates around site I, because of the stronger repulsions, we're going to have this term being more negative now. So in the case that we saturate the neighboring sites with adsorbates, then there would be a quite high rate for the desorption of this to the gas phase. So this was just a simple example, desorption of an adsorbate in the presence of repulsive lateral interactions. But how can we treat the general case? The general case can be treated in the context of the framework of Bronsted-Evans-Polanyi relations. These are linear scaling relations that give us the activation energy of an event with respect to the delta energy of reaction. So let's look at the energy with respect to the reaction coordinate just to understand what these relations express. So here is the initial state energy, transition state energy, right? So we go uphill and then down to the final state energy. So in this diagram, energy versus reaction coordinate, This is the activation energy, the difference between transition state energy minus initial state energy. And this is the delta energy of the reaction, right? So this vector here, final state energy minus initial state energy. So if this is the case of the reaction in the absence of any spectators at the zero coverage limit, and if we assume that the final state is a gaseous product which does not interact with the surface, then if we try to do the reaction again at a higher coverage, at a non-zero coverage, then we will see that if the interactions are repulsive, we are destabilizing the initial state. We are also destabilizing the transition state. The final state, we said it's a gaseous product, so it stays where it is energetically. And here is the new delta energy of reaction that we have and the new activation energy that we have. So the Bronsted-Evans-Polanyi relation for this reaction would correlate this activation energy with respect to the delta energy of reaction, and this would be a linear correlation. So for the forward event, the activation energy forward at the finite coverage limit would be equal to an activation energy at the zero coverage limit plus omega. This is a parameter called the proximity factor of the reaction, times the delta energy of the reaction at the finite coverage limit minus the delta energy of the reaction at the zero coverage limit. So this would be the equation for the forward activation energy. For the reverse, we have a kind of similar equation. We have the reverse activation energy at the zero coverage limit minus 1 minus omega, right, the same parameter here, 1 minus omega times the delta energy of reaction at the finite coverage minus at the zero coverage limit. What is nice in this framework is that the way these equations have been set up is ensuring that this equation will always hold, and this is expected because of the microscopic reversibility of our system. So going back to this is the delta energy of reaction at the zero coverage limit, which would be equal to the forward minus the reverse activation energy. If you rearrange, you will see that this is true. Delta energy of reaction is forward minus reverse activation energy at the zero coverage limit. So this gives us an equation to calculate this with respect to this and this. And then finally, if we subtract these two equations, we're going to find that activation energy forward minus reverse at the finite coverage limit is equal to delta energy of reaction at the finite coverage limit. So this really shows that we conserve the energy, and this is in line with the concept of microscopic reversibility and of course energy conservation. So this is the benefit of the parametrization of the activation energies from the Bronsted-Evans-Polanyi relations. So this way we can capture the effect of local reaction environment on the rate of the reaction, and this is convenient because this way we can simulate systems in which we may have a complicated influence of the spectator species on the reaction rate. So putting this all together, this is the algorithm outline for the advanced Kinetic Monte Carlo. So we have the preparatory operations where we initialize the data structures and the lattice, and we create a heap of all the microscopic processes, and then we enter the main KMC loop. While the time of the simulation is less than the desired final time, we advance the time to that of the top process, the most imminent reaction or adsorption or whatever event, and then we execute the corresponding process. So we first have to remove the reactants from the lattice. We have to also remove the processes in which these reactants participate, and also the lateral interaction patterns in which these reactants participate. Then we have to add the products into the lattice, and first we add the new energetic interactions, and then we update the event Q. So we add to the heap all the processes in which the newly added products, right, the products we added here, participate. So we solve the subgraph isomorphism problem to find the possible reactions that may happen now after we added the products. Of course, since we have added the energetic interactions into our simulation, the KMC simulation state, when we calculate the rate constants of these new processes, these would be the correct rate constants that take into account any lateral interactions between our new reactants, right, the products of the previous reaction, which are going to be now reactants for the newly detected processes, and the spectators. And finally, we may have to update the rates of existing processes if needed. So, for example, if there was a process that may still happen, we may need to update the rate of that process because the neighborhood, the spectators in the neighborhood of that process have been disturbed. There may be a reaction that happened that consumed some of these spectators. So the process now may need updating of its rate because of the change in the lateral interactions between its reactants and the spectators. So this is the final step over here, and then we repeat. So we then find the next process to occur, we execute it, do all these operations, and so on and so forth, up to the point that we reach the final desired simulation time. So this conceptual algorithm has been implemented into this software, Zacros, which I have been developing in my group for a long time. You can find more information about this in zacros.org in case this might be of interest to your research. So this brings us to the end of this lecture on kinetic Monte Carlo simulation. KMC is a rather versatile framework applicable to quite a diverse range of elementary events that can be simulated. So adsorption, desorption, reaction, diffusion, and other processes. So for example, LA-Riedel reactions and stuff like that. It's attracting a growing interest in the last few years. So you can see that the number of articles that mention the keyword kinetic Monte Carlo and catalysis or catalyst, etc. This number of articles has been steadily increasing. And the kinetic Monte Carlo method can provide a unique insight by bridging the molecular scale processes at the micro scale with observable phenomena at the meso and the macro scale, which have a dynamic component. So something changes in time. We can simulate all of these things and the sources of complexity that we discussed in this lecture using the kinetic Monte Carlo algorithm.